We are continuing our discussion of zeros of polynomials, and we have another theorem to talk about. In fact, we have a few more theorems before we're through with this chapter. And this next theorem is called the rational zero theorem. And before I give it to you, let's just think about an example to kind of understand where it comes from. So I'm giving you a polynomial here in factored form. P of x equals 2x minus 3 times 2x minus 5 times x plus 7. So in this factored form, we can easily see the zeros of P of x, right? Because to get the zeros, you set P of x equal to 0. And when we set that polynomial equal to 0, we have 0 equals the product of those three factors. So the only way this could be 0 is if one factor is 0 or the second or the third. And so I solve three little equations and I get x equals 3 halves, x equals 5 halves, x equals negative 7. And so the zeros of this polynomial are 3 halves, 5 halves, and negative 7. We can, you should be able to just about see those from inspection without even writing out the algebraic steps, right? Even from the very, very first line of the definition of this polynomial. Now, what we're going to do is we're going to multiply out P of x. And so I'm taking that same polynomial, same example, and first I multiplied the first two factors together and I got 4x squared minus 16x plus 15. And then I multiplied by x plus 7, and I didn't show the work here, I'm just showing the final result. We get 4x cubed plus 12x squared minus 97x plus 105. Now, what I want you to see is there's a connection between the leading coefficient and the constant coefficient and the zeros of the polynomial. This 4, that's the leading coefficient. If you go through the steps of the multiplication, it really came from multiplying the 2 in the 2x minus 3 factor times the 2 in the 2x minus 5 factor. So those 2's are related to the denominators of the zeros. Those 2's in the denominator of the zeros are factors of this 4. And when you think about where the 105 comes from, the constant term, that's actually 3 times 5 times 7. 3 times 5 is 15, 15 times 7 is 105. And so this 105 has factors 3, 5, 7, and the numerators 3 and 5, and we're also going to call that negative 7 a numerator because we can think of that negative 7 over 1, right, as in fraction form. So the numerators of the zeros are factors of 105. And that's really what this rational zero theorem is going to be all about. So let's just put this into words. The denominators of the zeros are factors of 4. This 4 right here, the coefficient of the leading term. And the numerators of the zeros are factors of 105, which is the constant term. And when we say numerator, we include that integer valued 0 of negative 7 in a numerator because we can write it as negative 7 over 1. And in here, when we talk about factors, we're saying factors could be positive or negative. We don't know exactly from the coefficients whether the factors are positive or negative. We just are going to have to allow that possibility, and you'll see we'll have to check both. So let's turn the page to the statement of this theorem now. So here is the rational zero theorem. And it's kind of a mouthful to write down. I'll show you a compact form in a second. Let f of x equals a n x to the n plus dot 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 plus a2x squared plus a1x plus a0. So that's a polynomial function with integer coefficients. So our coefficients a n all the way down to a0. A n is the lead coefficient. A0 is the constant coefficient. If p over q is a rational zero of p of x, where p and q are integers, and p over q is reduced, then p is a factor of a0, and q is a factor of an. Now, I'm just going to show you my yellow card I made for this one, because it's another theorem we're going to have to add to our yellow card list. You could kind of sum it up this way without all that notation. The possible rational zeros of a polynomial are going to have the form p over q, where p is a factor of a0, the constant coefficient, and q is a factor of an, the lead coefficient. Now, let's use this in an example. Let's see how we're going to apply this to certain problems. So here's an exercise. Our first exercise is determine all possible rational zeros of f of x equals 3x cubed minus 14x squared minus 7x plus 10. Now what do we mean by all possible rational zeros? Well, basically the rational zero theorem gives us a kind of like a short list of candidates, or a relatively short list of candidates for rational zeros. It allows us to narrow down the possibilities from anything, which is like an infinite number of possibilities, down to a somewhat shorter list of what you might call candidates or possibilities for the rational zeros. Now here's how we're going to apply this theorem. First, we just want to have a way of writing down what these possibilities are. And I sum it up this way. I write a p over q. And p over q, now I'm going to write p is a factor of a0. a0 is the constant term. So we're going to be looking at this constant coefficient. And so a numerator has to be a factor of 10. And I write factors of 10 because we're actually going to list them all to get all the possibilities. Q is going to be a factor of the lead coefficient 3. So we're going to list the factors of 3 in the denominator. And so let's think about what we have. Now I'm going to draw it in this kind of schematic kind of way. Factors of 10, well, 10 could be 1 times 10 or 2 times 5. And we don't know whether they're positive or negative. So we're always going to write plus or minus because it could be positive, could be negative. Now I had 1 times 10, 2 times 5. I'm going to write them in order, smallest to largest. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Those are all the factors of 10. The factors of 3, well, it could be plus or minus 1 or plus or minus 3. They're the only factors of 3. 3 is prime. Now, the possible rational zeros, so it's not certain, it's just a possibility. They're in this list. They're not every number in this list. They're just some of them. And what I'm going to do is I'm going to write down some fractions. I'm basically going to take each number up above over each number down below. And the way I do it systematically is I'll start with plus or minus 1, and I'll write it over the first denominator, plus or minus 1. Of course, that's just 1. I'll write plus or minus 2. And I'm going to go down the list of the factors of 10 over plus or minus 1 each time. Plus or minus 2 over 1, plus or minus 5 over plus or minus 1, plus or minus 10 over plus or minus 1. And now I'm going to go back and start over with those factors of 10 over plus or minus 3. So plus or minus 1 over plus or minus 3, plus or minus 2 over plus or minus 3, plus or minus 5 over plus or minus 3, and plus or minus 10 over plus or minus 3. Now, I'm not normally going to write it in this way. I'm going to write this down in a simplified way. So plus or minus 1 over plus or minus 1 is just plus or minus 1. In fact, any of these with denominator 1 are just going to be integer values. So I really just could write plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. I didn't have to write the denominator, but I wanted you to see the role of that plus or minus 1 in the denominator. So that's where all the integer possibilities come from. Then this next fraction, we just write a single plus or minus a third, plus or minus 2/3, plus or minus 5/3, plus or minus 10/3. And that's our list of possible rational zeros. Each one of these is two numbers, right? So 2, 4, 6, 8, 10, 12, 14, 16. We've listed 16 possible zeros there. There can't be 16. This is a third degree polynomial. I think you realize by now that there are just going to be three zeros probably. So when we actually try to find the zeros, we're going to probably encounter some of these. Most of them will not end up being zeros. So I think, again, I'm going to stop this video, and we're going to continue looking at this polynomial in the next video.